Oh, hey guys. Let me just put this down. It is about 3 o'clock on a Wednesday, and so that means it's time for my first full advanced econometrics lecture. Talking to you guys about regression discontinuity today. So let me head over to my computer, turn this thing around. All right, how do I look? Pretty good, pretty good. Okay, so today's lecture is mostly going to be on PowerPoint slides. I'm going to share my screen with you guys in a second, and then I'm going to cut in two different times, I think, to go to my whiteboard. I'll show you my little office setup. But let's go ahead and get started with the screen share, so you're looking at some actual material. All right. There we go. All right. The regression discontinuity, this is, so along with this lecture, I think you guys should take a look at the regression discontinuity chapter in Mastering Metrics, and also in Bailey. The Mastering Metrics one is probably speaks a little more to the causality and stuff, where the Bailey one focuses a little bit more on implementation. And the plan for today's lecture, originally, I was going to do two full lectures about regression discontinuity in class. A full one on Tuesday about what is regression discontinuity, how does it work, and then half of the lecture on Thursday sort of about implementing it, the do's and don'ts of kind of working with the data and kind of the nitty-gritty choices that you have to make to implement a regression discontinuity. I think the plan right now is that I'm going to go over the first half of that stuff, sort of the big picture, what is regression discontinuity, when is it applicable, what sorts of data sets does it work with, on the video lecture, and then we might have a kind of in-class discussion about some of those nitty-gritty aspects, and you'll practice some of it in your problem set as well. So really looking at this overview, I made these slides before COVID-19 hit, and I made these slides when I was still planning to see you guys on Tuesday, March 17th or whatever it was. For these slides, I think I'm going to go mostly through I've got my little annotate tool here. Mostly I'm going to talk about this stuff, the first half of the stuff in this video lecture. I won't be doing much annotation. Okay, so vocabulary that you should be familiar with after you're done with today's lecture. What is a cutoff, an assignment, or a running variable, bandwidth, polynomial, and sharp versus fuzzy discontinuity, although that last one, we're mainly going to be talking about sharp discontinuities today. The regression discontinuity is maybe my favorite. It's a lot of students' favorite kind of causal inference technique because it's so dang intuitive and kind of great to visualize. And it's always nice when you can see causality in a picture rather than having to just go through the econometrics of it. And the overall idea behind regression discontinuity is if there is some rule, some cutoff, some jump, some kink that exists in the world that is hard to control, and we'll talk about what that means in a second, that can be used as sort of a natural experiment. So the idea we're going to be working with a lot in today's lecture is the idea of, let's say, incumbency in an election. So it is not obvious a priori how much of an advantage it is to be an incumbent in an election. And you might want to kind of consider, if you're a politician or if you're a consulting firm or a lobbyist, you might want to consider kind of what's the mathematical advantage of being an incumbent. And it's a tricky question to answer, as we'll see in a second. But as we'll see, in elections where an incumbent just barely wins with 50.2% of the vote versus 49.8% of the vote, you might essentially be able to treat that kind of as a coin flip between the winner and the loser. Another example might be the PSAT. I think most of you took the PSAT at some point in high school, and if you get above a score, then you're a National Merit Scholar, and you get more mail from colleges and maybe offers of more scholarships along with the actual merit award itself. And if you're just a point or two below the cutoff, then you get nothing. And so if we think that students who are scoring 240 versus 242 on the PSAT are not all that different from each other, then this can be sort of treated as a sort of experiment where we can compare the outcomes of these two different groups of people on either side of what's going to be called our cutoff. Okay, so The Yeah, so the stuff we're going to talk about today is kind of this idea behind RD, and then the implementation stuff we'll get to later. So we'll dive in a little bit to the incumbency example here first. Let's say you want to quantify the value of being an incumbent in an election. How, maybe what percentage more of the vote should you expect if you're the incumbent? Think about this regression for a second to yourself. Pause the video if you want and ask yourself, if you were to run this regression, that is the percent of the vote that in this case, the Democratic candidate received. This comes from a paper that I'll be talking about throughout the lecture, where they sort of measured things from the Democrats' perspective. So all the observations in this data set were Democrats, and some of them had won the previous election and so were incumbents, and some of them had lost their previous election and so were not incumbents. This is for House of Representative races. And so think about the outcome is the vote share that the Democratic candidate got, and then the explanatory variable is whether or not the Democrat is an incumbent. Okay? So think to yourself, what are going to be the omitted variables here? Why would the estimate of beta 1 hat be biased? And I guess now I'm going to show you on the board. Stop sharing that. All right, so now you should be looking at me. Zoom over to my whiteboard. And I'm moving my microphone a little bit too. Okay. All right, so you can see the board. I'll go up a little bit more so you can see me a little better. I know you guys have all been missing my face. I've been missing seeing you on my Tuesday and Thursday mornings as well. Okay, so we are interested in the impact of being an incumbent on the percentage of vote that you get the next year. It's pretty clear if we're drawing a kind of causal diagram, it's without too much debate that being an incumbent might have a direct effect on the percentage of vote that you get. The pathway of the arrow here is pretty clear. Let's think, though, about, in that model that I showed on the slide, what might be some of the things that are going to be in the error term, things that we're not controlling for in the model. So that could be things like maybe the charisma of a candidate, the funding of a candidate. In other words, better candidates are usually going to end up as incumbents. If we're just looking at the impact that being an incumbent has on a vote share, who are the incumbents in an election? They tend to be the best politicians. The people who win elections tend to be better politicians than the people that they beat. And so you might, if you just look at the relationship between incumbency and vote share, you might sort of mistake the impact of incumbency for the impact of being a really good politician. In other words, there is correlation here that kind of goes both ways between being an incumbent and a lot of omitted variables that we're not accounting for in our model. Right? So the idea that we're going to be playing with, though, is that we can break this chain of causality. Is there's a step in between kind of these traits and becoming the incumbent. And that step is the percentage of the vote that you got in the previous election. So we'll call this previous percentage. And the percentage vote that you got in the previous election, that determines whether or not you become the incumbent. If you got over 50% in the prior election, then you're the incumbent. If you got under 50% in the prior election, then you're not the incumbent. It's as simple as that. So the idea of kind of a regression discontinuity, and we're going to talk about it in this one specific case, but this sort of diagram could apply to virtually any RD setting, is that if we control for previous vote share. If we hold this constant, we hold this constant in our model, we can then uncover the causal effect of incumbency on the likelihood of being reelected, because all of the things that may be in the error term in this case, they don't act directly on being an incumbent. They act through your previous vote share. And so by controlling for previous vote share, we are essentially blocking off any backdoor paths, any omitted variables paths to the outcome, and we end up just with a causal path. So that's the sort of visual or diagram version of regression discontinuity. The trick, though, is that this is only going to be true, this kind of causal thing is only going to be true for elections that were close to 50-50, close to what is sort of the cutoff for deciding whether or not you become an incumbent, okay? So we'll get back to the slides. I need to share my screen with you guys again. All right, here, almost every regression discontinuity research paper you ever read is going to have a diagram that looks like this. Here we have on the x-axis is the percentage of vote that a candidate received in kind of the current election, in the election in question. And no, I'm sorry. The y-axis is the share of the vote that a candidate received in the following election. The x-axis is the share of the vote they received in the previous election that is normalized around 50-50. So a 0 means that you received exactly 50% of the vote. So all of these blue dots that you're seeing on the screen right now, these are candidates who in the prior election from 2 years ago just lost and are rerunning again. And then all of these blue dots in the election, or on the left-hand side of the graph, are dots who ran in the previous election, got over 50% of the vote. As you can see, when you're just plotting the data, this is just a scatter plot of the data, it's not a regression or anything like that, there's a jump in the likelihood of being elected right at this cutoff. The difference, the probability of being elected in this year's election for someone who, say, got 30% of the vote last time versus 35% of the vote last time, yes, the person who got 35% of the vote, here I'll annotate, maybe this dot here is someone who got 35% of the vote, whereas over here is someone who got 30% of the vote. Oh, that handwriting's bad. Sure enough, the person who got 35% of the vote last time is more likely to be elected on average. The slope of this line is positive than someone who got 30%, because the person who got 35% probably has more charisma, better fundraiser, is a slightly better politician than the person who got 30%. All these other omitted variables from the model. But it's a pretty marginal increase for every value from someone who got 0% of the vote all the way up to people who got 49% of the vote. Then, at the cutoff, at 50%, there's this huge jump in the likelihood that you get reelected. The idea of a regression discontinuity is that if we sort of compare these people to these people, these dots to these dots, the sorts of politicians who were getting 49, 48% of the vote to those who were getting 50, 51% of the vote, the difference in outcomes between these two groups can solely be attributed to incumbency. And so what the regression is going to estimate, what's going to be called beta 1 or beta 1 hat, is the true causal incumbency effect. It's an incumbency effect that is free of all of the other omitted variable things, the charisma, the fundraising ability, the demographics of the district that might also drive an incumbent to be more likely to be reelected. All right, the form of a standard regression discontinuity model you can see at the bottom of the screen, which is that beta 1 is a dummy variable for whether or not you were an incumbent. Beta 2 is then what's going to be called our assignment variable, or the continuous variable, that is how far above or below the cutoff were you to start out. And so in this case, the cutoff is 50%, so we take your vote share from the previous election and subtract 0.5 from it. The assignment variable is always just kind of by convention. It doesn't have to be, but by convention is going to be demeaned kind of at the cutoff. All right, and then this is probability that the Democrat wins. This is winning the previous year share of vote. So the first graph, this was your share of the average share of vote in the next election, whereas this is then the probability of you winning the next election, which are kind of just two different ways of looking at winning. But we see whether we're defining this as the incumbency advantage in terms of how many more votes should you expect, or the incumbency advantage in how more likely are you to win the following election. Those are two kind of different ways of measuring a similar phenomenon. Sorry, I'm going to remove my microphone back a little closer to me. Okay, the standard, well, you'll note that your two textbooks don't agree on how to define regression discontinuity, but this is using the Bailey notation. And this is fairly universal notation, is that TI is a dummy variable that's going to denote treatment. So in this case, it would be, were you the incumbent? Yes, T is 1. Were you not? T is 0. X is then going to be a continuous variable that's called the assignment variable. And so that is going to define what was sort of your relative value of the thing that's going to determine the treatment. And so in this case, there's a cutoff, C, and so TI is going to be equal to 1. You're going to be the incumbent if your vote share in the previous election was above the cutoff. So in this example, the cutoff would be 50%, XI would be your vote share in the previous election, and TI is whether or not you're the incumbent. The standard form for regression discontinuity is that we are looking at the effect of treatment of the TI variable, but we are controlling for the assignment variable. It's critical that we have beta 2 and the x1 in the model, that we control for that assignment variable, because then that shuts off all of the other potential omitted variables bias. The incumbency is a particularly clean use of regression discontinuity. This graph sort of is, I think this is from fake simulated data, but shows what sort of the messier world that regression discontinuity often takes. Especially when the outcome variable is maybe not just a 1 or 0, did you win or not, there might be lots of people, right? There's lots of blue dots here just below the cutoff. You're comparing, maybe 40 different people just below the cutoff. I should maybe not have my line be blue. This group of people just below the cutoff, you've got 40 people down here, you've got 30 people just above the cutoff, and sure enough, some of the people below the cutoff are doing better than some of the people who are just above the cutoff, but on average, there's a discontinuous jump right around the cutoff. That's what we're taking advantage of in a regression discontinuity. And exactly, that bump is the causal effect of the treatment. So the idea behind regression RD, which I feel like I'm repeating myself a lot here, is that right around on either side of this cutoff, you essentially have a natural experiment. It's effectively random who is on either side of the cutoff. The important thing when it's coming to ask yourself, is a particular question, is a particular data set I have appropriate for regression discontinuity, is it is critically important that the cutoff is hard to manipulate. In other words, that the person being observed or the thing being observed doesn't have too much control over which side of the cutoff they're on. It's hard for a politician to get exactly 49.9% of the vote versus 50.1% of the vote. They don't have too much control over exactly where they are on that margin, which makes kind of elections a ripe venue for using regression discontinuity. Whereas if it's, I'm trying to think of another setting where there is some cutoff. So there's another setting that might be less appropriate for regression discontinuity, might say eligibility for some sort of welfare benefit, where what's important is for whether or not you receive welfare is what your income is. And so if your income is below a certain threshold, you get welfare. If it's above the threshold, you don't. Income, we tend to think might be a little easier for someone to manipulate than, say, election vote share. people, if they know that, oh, if I earn over a certain amount, I'm not going to get any more welfare, they might intentionally only work enough hours up to that point. People might fudge the numbers, right? They might just misreport on their taxes or something like that. So something financial could be a more difficult situation for using regression discontinuity than something like an election. All right. To think about regression discontinuity in terms of the potential outcomes framework, this is I really wish we were in class for this, but I'm gonna go back to the board and give this a shot. So screen share, back to the board. This is where I've got to move my microphone. Right. This is where the annoyingness of writing formal mathematical notation in PowerPoint meets the downside of bad lighting, as I'm kind of choosing between between a rock and a hard place, I guess. So the standard potential outcomes framework that we kind of use for causality is this idea that what we want to do is we want to observe. We can never observe the same person in two different states of the world, and so we want to come up with situations where we are as close to observing sort of two groups of people that we think otherwise have all else equal as possible. So in standard notation, we have that what we tend to observe yi given ti equals 1 minus minus the expected value of yi given ti equals 0. So what we can observe in the world is outcomes for people who got the treatment minus, and we can then subtract outcomes from people who didn't get the treatment. This is the observed difference between treated and non-treated people. And we know, this is going to be in your lecture notes from lectures past, that this is equal to the expected value of y1i minus y0i given ti equals 1 minus the expected value of y0i given ti equals 1. Should that be... Yeah, no, that's right. So minus, plus. This is then going to be minus the expected value of y0i given ti equals 0. Let's make that a square bracket. Okay, so what we are able to observe, which is the mean outcomes for people who were treated minus the mean outcomes for people who were not treated, is equal to the true causal effect of treatment, that is, the causal impact on those who were treated, the difference between their counterfactual outcomes, plus this second term here is selection bias. And that is, in the world where treated people had not been treated, how different are they on average from the people who were never treated? Right? So we've seen this a bunch before. The idea is that we need to eliminate the selection bias. What we want to uncover, this is our causal effect. Okay? You can just barely see that. Let me tilt this down a little bit. But then you see less of my face. I mean, trade-offs to everything. Okay. So the theory behind regression discontinuity is that the expected value of yi given that xc is going to be, so I'll call this equation A. So this is x sub c is less than xi is less than xc plus delta. Sorry, so x sub c is going to be the same as the cutoff here. So x sub c equals capital C equals the cutoff. This is just the value of the running variable, the percentage of vote from the previous election, in this case, that's equal to the cutoff. The potential outcomes framework stuff tends to be more of the mastering metrics world. Ingres and Pischke focus a lot more on that. They use x sub c, so when I'm doing kind of more of a version of their model, I'll use x sub c. When I'm doing more Bailey stuff, I'll use c. All right, so this is the expected value, the expected outcome for an individual whose actual assignment variable, so this is maybe their actual election result, is above the cutoff. Sorry, this all is above the cutoff, but just barely. It's only above the cutoff by delta. Delta is some small number. So this is people who receive just a little bit more than 50% of the vote. And this A thing, we can say that this is approximately equal to the expected value of y1i given xi equals xc. For people who are just barely above the threshold, their average outcome is representative of the average outcome for people who get the treatment, who are above the cutoff, but whose assignment value was exactly at the cutoff. Meanwhile, we're just going to do the same thing for people below the cutoff, that the expected value of yi given that xc is slightly greater than xi is slightly greater than xc minus delta is approximately equal to the expected value of y0i given that xi equals xc. Then if we take A minus B, and the nice thing is that we can observe, A is something we can observe. We know who these people are. These are people who got treated, who are just above the cutoff. And we can observe B. We don't have to do any fancy recalculations. These are people who are just below the cutoff who did not get treated. A minus B then gives us the causal effect that we are interested in. Okay, so this is sort of, or I should say, the limit as delta tends to 0. The limit as delta tends to 0 of A minus B then gives us the causal effect at the cutoff. It gives us the causal effect, in this case, of incumbency for the sorts of politicians who get around 50% of the vote. All right, so hopefully you more or less buy into this idea of regression discontinuities as a sort of natural experiment, that people who are just around some similar cutoff can sort of be used as if they had been randomly assigned the treatment. One of the most powerful things about regression discontinuity is that even though it uses this idea of a cutoff, it does not speak to causality only for people at the cutoff. The external validity of regression discontinuity is really, really strong. Let's think about that in terms of the National Merit Scholarship and the PSAT. So to get the National Merit Scholarship, you have to get a score above 220. So the sort of idea of an RD is that you're comparing people who scored a 221 versus 219, or maybe people who scored 221, 222, or 223 to those that scored like 217, 18, 19. And then that's a pretty valid natural experiment. Those people a priori were pretty similar students. It kind of takes away the normal omitted variables. This kind of regression discontinuity then is a study of the impact of money on education. How much does kind of a shock to your income, a shock, or maybe a shock to the price of school, if the scholarship reduces the price of school, how much does that do for some of your key outcomes? Sorry, I had to move the microphone again. key outcomes like the likelihood that you go to college, the likelihood that you graduate from college, your income after graduating. The cool thing is that that number, 220, the cutoff, is also itself kind of random. If you ran this study and you found that there was an impact of winning a national merit scholarship on education, because 220 was not like some deliberately chosen number, it's not that we know everyone's a genius above 220 and not below. You could reasonably say, hey, had the cutoff been 215, then probably, and we had done the study on people who had gotten just below 215 or just above 215, probably we would have found a very similar effect for those people. Or if the cutoff had been 230, probably we would have found a very similar effect for those people. In other words, if you find that there's a positive impact of money on education when the cutoff happens to be at 220, your study isn't actually just saying that people around this cutoff benefit from money. It is saying that the impact of money on education, the impact of reducing the price of college on educational outcomes is globally significant. It can apply to anyone on the spectrum of PSAT takers, say, because why, again, if 220 is some somewhat arbitrarily chosen cutoff, if we find an effect there, why wouldn't we expect it to apply anywhere else on the distribution? It might be the case the size of the effect might change a little bit as you move along the distribution. Maybe the effect's a little bigger for people who score an PSAT score of 220, and if we had gone up to 250 or 260, then would have gone down. But generally speaking, regression discontinuity has really good external validity. All right. A little more kind of formal modeling is that the error term we know is correlated with the assignment variable. In the case, we'll switch now and use kind of the PSAT variable outcome case. So here the cutoff is going to be, was your PSAT score above or below 220? Yes is 1, no is 0. The assignment variable is your PSAT score. So x1 is the PSAT score. We know that x is correlated with all sorts of other things in the model. So it's correlated with your family incomes, it correlated with the quality of the school, it's correlated with the neighborhood you come in. Normally, we would need to control for all of those things in an OLS model to get a causal effect of the impact of a price shock or an impact of money on educational outcomes, not with an RD. So if we estimated the model with only the treatment variable, that would be bad. But when we include X in the model, X sort of absorbs all of that bad. So these slides are really kind of formalizing what I was saying earlier. So the conclusion here is that it is okay for the error term to be correlated with the assignment variable. In this model, beta 2 is not causal. We're not getting an estimate of the causal impact of a 1 unit increase in your PSAT score. That estimate is going to be contaminated with, well, higher PSAT scores are correlated with higher, family background or teacher quality, blah, blah, blah. What we are getting is a causal impact of beta 1. So it's okay that beta 2 is not causal. The thing that needs to not be true is that it's not okay for the error to jump at the cutoff, that people just above the cutoff all happen to be particularly lucky people or people who have higher family incomes or other non-measurable things. The nice thing of what's part B on this slide, this kind of key assumption of regression discontinuity, is that it's testable. You can normally look at other variables and see if they jump at the cutoff. So it should, for example, in the PSAT example, it should not be the case, say, that the average family income of people just above the cutoff versus just below the cutoff is noticeably different. It should not be the case that the quality of schools of people just above the cutoff or just below the cutoff is noticeably different. It's okay if it's kind of moving gradually. We'd expect that there's maybe a positive correlation between family income and PSAT score. There just can't be a discontinuous jump. Putting RD in context with OLS and instrumental variables, regression discontinuity is actually sort of a subset of instrumental variables. It's very similar in spirit, but just kind of uses the specific sort of cutoff. All of these are cases where we are doing our best to control for measurable factors to try to get a causal estimate. Option 1 up here, true exogeneity would be a research design experiment. That's often very hard to achieve. So normally the next best thing that you can do is control for measurable factors. OLS, we know, without sort of some identification strategy, is often going to suffer from omitted variables bias, whereas in instrumental variables and regression discontinuity, you have to make weaker assumptions to have a causal impact. With instrumental variables, it needs to be the case that your instrument is not correlated with the error term, which is usually a weaker assumption than that all of your x variables are not correlated with the error term. And then in regression discontinuity, all you need to assume is that the cutoff is hard to manipulate and that the cutoff was essentially arbitrarily placed, that there isn't some entrenched difference between those 221 scores on the PSAT versus those 219 scores, and that students have a hard time manipulating. You don't have much control over your PSAT score within a few points. Obviously, how much you study dictates whether, kind of within a 10 or 15 point band what you get, but it's really hard to control kind of down to those last couple points. When it comes to regression discontinuity, it is important to sort of control for the running variable in the right way. So this diagram shows what kind of can go wrong. The top graph is where the relationship between the running variable, the assignment variable, and the outcome is linear. The middle graph is one where the relationship is polynomial. And then the bottom graph is one where the relationship is polynomial, but the researcher used a linear model to measure it. You can see so the takeaway of this graph is that in the bottom chart, if you used the wrong model, if you used a linear model when actually the relationship was curved, you might estimate a discontinuous jump in the data, when actually it was just kind of a slight marginal change in slope for a little bit of time and then flattened out again. So I guess we're going to talk about that more live in class, of sort of how to choose which world you're in and the flexibility of the model. Regression discontinuity is used in policy evaluation a lot because lots of policies just barely pass. There's politicians who barely get elected. There are bond measures that just barely pass from maybe a statewide initiative. And so oftentimes this can kind of be used in an RD setting for evaluating policy. Okay, sorry, I'm kind of making sure that I'm done. Yeah, so I think the rest of this is what I'm going to want to talk with you guys about live. So I'll cut this lecture off here. All right, so now you're back with me. Read your book chapters, read the assigned papers, and I hope everyone is doing well wherever you are during this remote spring semester that we have. So take care.